Okay, so here's my presentation. I'm gonna talk about like circuits writing today. Okay. So the title of it is Programming SDK for Halo2 Frontend, and it's based on the circuits tools, which is not yet a standalone repository, but it's gonna be developed by our circuits developer, basically Brax and I. So the motivation of the whole thing is the fact that it's difficult to convert programs into equation. As we know that like if we have some programmatic logic here, and we have like X and Y, and we have some branches, if and else, then how zero knowledge proof work is we have to convert that into this type of arithmetic representation, basically equations that look like this. And then finally, after some moon math, it gets converted into something down here. And the reason why snarks are able to compile everything into like one step of verification is because like it converts everything to basically polynomials and verifies at that one single point, which is not my focus today. Because what I'm going to do today is going to talk about the front end of circuits writing. So as I just explained, the back end of any zero knowledge proving system, which is like, in our case, Halo2, which is the framework that we use for DKEVM. So the back end of it is basically the cryptographic proof protocol that is done by like professors and researchers and people like Alexi and our team. Examples of which include Plonk, Bulletproof, and Sonic. And the front end of it is the process of how we convert this to this. And this process is actually in some way back-end agnostic. So the front end stands for the first round of conversion from program logic into mathematical representation, at which we call arithmetization by the ZK term. And if you have saw like Dan Bonet's presentation, you've probably seen the diagram before, which summarized most of this process of how we compile a DSL program, which is like a domain-specific language that includes Circum, Socrates, Leozane, Cairo, and Lua through like a compiler into some snark-friendly representation, which includes R1CS, AIR, or Plonk. And after that process, it gets compiled into like one single pi, which is our proof. And the heavy computation happens here. And in the Halo2 case, though, we're not using a DSL. We're not using a language. That's why people say writing in Halo2 is like writing assembly. You'll see that for a second, because this is how Halo2 circuits look like. This is an example of Plonkish arithmetization circuits. Plonkish stands for, it's from like the protocol Plonk. And this diagram below is what I just copy and pasted from US Notion document. And this one proves the public the RLP decoding of our block hashes or whatever of the block fields. So if you see closely, the vanilla Halo2 circuits was written in this way. Usually people design it with like vertically with all these columns representing some incremental values or decremental values. And the advice column, which is like the data that we read in, goes into one of these columns. For example, like by the end, if you see the bytes columns here, these are basically raw data. And here, if you see like the orange bracket in the middle, this is basically one constraint that we apply to the data that are in this table. So basically it's saying we have a RLP RLP sum, RLP remaining length column that record how many bytes that we still have in the block data that we're going to read. And then we also have like on the left hand side, which it says like 4 and 21. This is like the length of that one data field that we're reading. And the constraint is basically 263 minus 21 equals 242. So we're constraining that at each incremental step, the upper value equals like something, the lower value equals the upper value minus the one on the value on the left. And then as long as the queue enable, the enabler is turned on, which is on the right hand side for this one value that is over here, as long as this is turned on, this one single constraint is going to keep applying throughout the whole table until the end. At which, if you see like things got decreased to 0, and then we have nothing else to subtract. So this is like the intuition of how circuits design work. And imagine you're going to use this thing to write the entire ZK EVM. It's going to be difficult. And the codes actually look like this. This is like another code expert that I copy and pasted from the Halo2 example. So like the vanilla gate specification looks like this, which it constrains, for example, the column Z should start with 1, like Z0 equals 1, like the first array index of Z equals 1. And then it should end with 1. And then it has like increment by some like transition rules. So this is how circuit writing work. We're applying constraint expression to columns. And imagine we're going to have like highly dynamic data and super, super complicated logic. It's going to be difficult to write it this way, right? So that's why it brings us to like our implementation of like circuits tool. In order to like build constraint expression, for example, we have like branching. How does branching work in circuits? So it basically work like this. If we have like if A, then X plus Y, else then X minus Y, it works with like this expression A times X plus Y plus 1 minus A times X minus Y. And A must be always 1 and 0. Well, if you take 1 sec, think about this expression, you'll see that like if like our advice data actually takes branch true, the true branch, then this expression will return X plus Y. If A equals 0, then this sub expression will return true, and then the whole thing just return X minus Y, which represent the logic function that we're writing here. But what if we have lots of branches? Think about we have like if A, if B, and if C, and then it turns out, and then we walk into one branch. And what if we actually don't take one branch? Well, what if we go to some other branches? We're gonna represent like everything in a giant equation that looks like this. So how do we do that? Like we need some tools to simplify this process so that our circuit programmer don't have to hand write all these things. So here is what we built. So a stack machine to model the behavior of conditional branching, which is what we're doing like nowadays in like the actual runtime execution of our modern computers, right? You push and pop stacks. That represents you enter through like a call frame of a function. And in terms of branching them, think of the scenario that are here in the push pop like these like tables. So if we enter some branch, let's say we have condition A1 and A2, and then we push this condition onto our stack, and then we also push constraint B1. Let's say B1 is equals X plus 1, and A1 is like the true and false statement. And then as we enter deeper and deeper into the call stack or into the branches, we push more constraint and more condition. And as we exit the branches, we pop. And by the time we pop, we apply the condition onto our constraint, in which at this point, when we exit out like these two, the first layer of branching, we have A3 multiplies B4, B3, and B2. And then when we exit everything completely, we are ended up with like raw equation that looks like this, the final columns. And our code base is actually implemented in this way, like CB, which stands for constraint builder, push condition, and then that's where we enter a branch. And then when we're like running the closure function of this like return statement, then after that we pop the condition. Then and at that point we apply everything back to one single expression that we finally built in the raw code here, where it's like create gates, and by the end of the day, it's going to return like a giant condition by the end here. So if we have like this type of paradigm, it's kind of easy to write some domain-specific language or some syntax trigger to wrap around this. So that's what Brax originally came up with, and which is what I've spent like the last few months optimizing, which is this macro thing. So this if exclamation mark will basically do like the push condition that is like in the code here. And then, so if we see like this is one like a screenshot from the MPP circuit. So we're saying like if key is odd, then do this, or else we do that, right? So basically what if you expand the macro, it goes like push this if key odd condition, and then return where it returns this thing as the return statement, and then as the pop, like we generate this if key odd multiply with the stuffs that are inside. And then in the else condition, it will be 1 minus if key is odd, multiply like the whatever things that are down below. And in this way, we can write like very, very complicated nested loops or nested condition branches with the macros. And all of the code is right here in the ZK-EVM repo. If you guys are wondering why does it take so long for MPP to be merged, it's because it includes everything here. And also like the upcoming things. Yeah. So one downside of this is, as you can see, like if we ended up with like popping everything, these expression here could potentially get super, super long, which results in super high degree custom gate that Plonk cannot handle, where it would just like take very too long of a time to run. So we also come up with this degree reduction technique, at which we recursively go through every single condition, every single expression that we generate. And before we actually push them into Halo2, we perform this degree reduction operation that we recursively like iterate through each different branches of the expression. And we loop through it until the degree of it is below the certain limit that we have. For example, in the original statement here, it has like a degree of 3, and let's say I set the maximum degree as like 2. Then after the split, we'll down like in the leaf branch here, like we'll be ended up with like degree with like at most 2, and then we'll store the newer expression into the cells. And each branches represent an equality constraint between whatever that is above and whatever that is below. So what I'm saying is that, so I have to constrain the multiplication of C times D plus E, and the expression F actually equals to this expression that is up here. Yeah. So like it's, on the surface, when users are using this will be like, they won't feel they don't need to like take care of any single like process. These are all being handled automatically by the backend. Yeah, there are a lot of difficulties with this design. For example, we have to apply the correct condition back to each split statement that are in the leaves branch of the degree reduction tree. And then we also need to assign the value correctly, which is why we basically overwritten the region thing that are in Halo2 in order to remember the value that are being stored and the shape of the topological shape of the tree. And then when we're assigning the word, we have to trace down the tree back again in order to assign correct value at the correct place. And once I was messing with this, and I came up with a lot of bugs. And Brax had to fix it with some other hacky thing. But yeah, it's a very complicated system that users don't feel. So this is constraint. And as you can see, in order to achieve this constraint system, we need very specific cell allocation. We need to query data at specific position. If we went with this original Plonk design, that we have one variable per column, it's going to be terrible. So what we're going after is a cell-based approach where we need to query a specific cells at specific location, which brings us to data allocation and cell manager approach that I'm going to talk about later on. So traditionally, like I said, a column-based approach will waste a lot of columns. Let's say we have these two computation that we need to do, A times B plus C equals 0, and D equals B plus 1 at all rows. And then this A, and then the first expression is only activated in the first row, which is the red over here. Yeah. So all we want is the result of this computation at this one single row. And this needs to hold true for all rows. However, if you see what we end up with, it's all these zeros that are right here. What does that mean? That means that we're wasting computational power. We're wasted basically 9 cells as a whole. But think about it. What if we can just query one single cell at one time based on what we need, right? So, which brings us to this cell-based approach. In the cell-based approach workflow, we have a cell manager that actively queries cell as we need. And the cell manager is going to distribute cells whenever the user calls it. And the resultant layout of the circuit will look like this, right? We have 3 times 7 equals 21. And then the rest of it holds true. That goes down to all the way down to the bottom of the table. Yeah. So, and in this way, we only wasted 2 cells here, which is inevitable because these cells haven't been queried yet. But there are certain constraints to this. The scenario of the cell-based approach only holds true when all we need is a temporary register for some computation, and the actual layout of circuit doesn't have to make sense, right? And actually, in a lot of cases is like this. For example, in EVN computation, where we are only computing a temporary equation, someone's gas fee or someone's a temporary value, which only appears one time. We don't want to query something, query another column, initiate another column right here. Yeah, but if you want regularity in the value that changes across row, for example, we're calculating a accumulating value of someone's gas fee or someone's account value, then we might as well use a column-based approach. But the big idea is memory allocation is register. We want to switch the Halo2's programmer's mindset from column-based to cell-based, where you query, register, or you utilize your register in your computer as you need. You know what I mean? Not initiate a lot of things, but which ends up with a lot of computational footprint. And this is cell manager. The cell manager is also like in one of the folders in the ZK EVM circuits. Yeah. So, and the next topic, which is my favorite, is lookup and memory. As you might know, like Halo2 is famous for lookup tables, and lookup is a very powerful technique that these ZK researchers came up with a long time ago. Because before we only had constraint and computation. Lookup is the first thing that proves subset argument and range check that in a different way comparing to how we prove the correct computation of some existing expression, right? And this is complicated, but it basically says that column A, so whatever data that are in column A is a subset of whatever data that are in column S. If we're able to prove this thing fast, it will give us the power of preloading some static data into the system and quickly look it up. So preloading static data meaning we can insert some data into column S first and commit to those data, and then when we're doing computation in column A, which is our dynamic data that are residing on this side of the table, then we can quickly look it up so that like this could be like a range check. This could be like like the static fixing address in your computer. So we're one step closer to mimicking the full computational power of your laptop, right? So a scenario of this could be, first of all, fixed lookup, which is the example which was what I was talking about, like the fixed memory. A fixed lookup often have like the two following purpose for proof time witness. The first one is data validity. For example, we have some existing name list that are in this table. We want to check that Alice 15, the female, actually exists in the name table that we had before, right? We want to prove that Alice is valid. And this is actually how we do like a lot of things in the ZK EVM. For example, like K-check, because whenever we load data, or like if we want to perform K-check in ZK EVM, it's like K-check is the most difficult things to do, like Lisa just talked about. We can't hook it up. We can't hook up a K-check proof whenever we access it, right? The most efficient way to do it is to generate like some sort of batch K-check proof, or like proof that all of the K-check operations are correct, and store the data in a table. And then when we're actually accessing the K-check table, we use these like data validity checks to look up into the existing K-check table that we've already verified with some other proofs. So this is like the first scenario. And the second scenario is the range check, which, for example, we want to check that Alice is under 20 without revealing Alice's actual age, right? We just need to look up value 15 in the table that ranges from 1 to 20. If 15 is indeed a subset or exists in the bigger set, then we think that Alice is legit. She's like under 20, right? So this is fixed lookup. As you can see, is looking up into some fixed data that we preload them into the system. Yeah. And another more interesting use case is dynamic lookup. Think about like the scenario where like Alice is like going to the bank and then she has a bunch of bank transaction. In this case, like for example, we only have access to a single day's data. We don't have like the entire transaction history. We kind of want to look up to the fact that something like Alice indeed has like $500 in the bank. but we don't know like when was that stored, or we don't even have the access of data for that or something. Yeah, so all we need to do is to look up into the table. So whenever Alice store her money, we store this data into the lookup table, and then when Alice is like retrieving her money, we perform a lookup into some table. If $500 actually exists somewhere, then we think that Alice has that money. And of course, like some other constraint needs to be applied. For example, you need to prove that you're storing and loading data at the right time. We can't just like look up some random $500 in the bank account and think that's Alice. Maybe Alice had that 5 years ago, but not anymore. So there's like more subtle constraint that we need to consider, but this is the general idea that this thing gives us the dynamic random access memory power that we can have in the ZK EVM. So, like I said, for the memory proofs, we're able to mimic the computation environment of a physical machine one step further with fixed lookup representing static memory and dynamic lookup representing the RAM. And here's the illustration of how it works for dynamic lookup. So one gray arrow represents one lookup constraint. And basically what happens here is if you see this like A1, B1, and C1, these represent dynamic data that we're generating at proof time. And the tree-like structure with this like grayish line represent the random linear combination of these data into some fixed column, into some fixed cell that's here. And so by the end, when we're like generating the lookup with this method, we're generating from one cell looking up into some other cell. But behind the scene, there's actually RLC and also degree reduction that this cell in itself has very high degree if we just store like the raw data in here. That's why we need to apply like the tree method here to split it. And then finally end up with a value that stores here and looking up into the table side. So in this case, like the data aspect and table aspects are like mirroring, because both sides are dynamic. Because like Alice can store $500 at any time, and Alice can load $500 at any time. So this is like dynamic lookup with RLC and split. And we also have other lookup paradigm, which we have here, dynamic data looking up into fixed table. So these could represent like Alice name tag values, like name, age, and gender, like something like this that are fixed that we store in the table before, and when we do a RLC of like all these random numbers, so basically combine them, and then we perform the same lookup. So the reason why we do RLC is to decrease like the width of the data that we need to look up. So like here, if after we do RLC, it's basically one expression looking up into another expression instead of three looking up like three. You know what I mean? So this is like another method. And as far as I know, this is like the most common lookup that is being performed in the current ZK EVM design. So basically out of the table has one API that generates the table expression, and then all of the data are being combined and stored in like one cell, one column. And from here, like one lookup constraint is generated to cover all of the lookup. So like comparing to like what's happening here, because like it's all dynamic. In this case, then we have to like generate lookup constraint every single time. Whereas in here though, since like we know that table is fixed, and then we can tag one single cell. For example, we tag one single column as like the transaction column. So like all of the transaction data will be stuffed into this cell. And then by the end of the day, we just generate one lookup constraint that covers all of the existing transaction in the proving logics. Yeah. So these are the lookup, the optimized lookup that we have. But we also have like in place lookup, and which is very more commonly used when we have like range check or like byte checks. Consider if we have like one line of bytes that we need to constrain all of them to be like bytes, like they have to be less than or equal to 257. Then if we combine everything like we do it before, then it's going to generate a large memory footprint, and it's not necessary at all. So what we do is we perform in place lookup, that we just use the expression as it is to like look it up to the table. And then the two scenarios down below are the vanilla lookup by Halo2. So if you basically don't do anything, if you don't do RLC and don't do degree reduction, you end up with ABC looking up ABC. So the ones on the left side, this is the vanilla lookup that you have in Halo2. So look at how many optimization that we do. And if anyone's interested in some of the work that we're currently doing, so basically I am working on like a uniform API for people to perform all these type of lookup. Because it's vague how data is being looked up, because like the ZK EVM has so many different implementation and people are looking up data in different ways. Like what I'm trying to do is to come up with a uniform macros to represent different lookup style and generate the lookup data in the correct way. So like maybe what I want to do next is to have like some sort of pool based approach where we like store like some data type of cell manager data and some data type of table data, and then have like the flags on, and then have them like look up to themselves automatically. So like the constraint builder will be able to build lookup in the correct way as it is, as user specified, without the front end, the user to consider too many details, like how it's going to be performed in the back end. So that's our goal. And so what we have so far is we've already handled logic, which is like branching, and also like how do you build constraint, and data, which is the allocation of register, and memory, which are the lookup. So we are closer to a Turing machine, a complete Turing machine implementation now. But the problem remains, as like I said, we're still having very high degree expression, even with the degree reduction. And also we need to optimize lookup runtime, the lookup limitation. Because imagine if we have a super, super long lookup table, basically these are left to the back end. We need faster back end to handle all of these front end expressions and lookup that we generate. But I think in general, since like all these methods are backend agnostic, I think what we're working on is very promising within the entire ZK space. And then we're also like collaborating with Shahito, which is another project that is doing like Halo2 DSL, which I honestly think that our system is better because it's macros, which expose the backend back to the user whenever he or she wants. We don't like wrap up the entire Halo2 and just give you like something like circom, which is like super dumb. And then you don't see how things are operating. You still have a lot of freedom to optimize your own circuits. So this is our work in the ZK team, and this is my presentation. Thank you.
Thank you so much, Cecilia. It was like very deep and very wide and very cool. Wow, I'm really impressed. Does anyone have any questions?
I have one question and one executification. So a question. First, thanks for the presentation. It was especially good that some basics of lookup tables were discussed, and the question by itself. So if we're talking about cell manager, it's aimed at allowing programmers rather not to work on columns, but to allocate some relative places of cells.
Yeah.
I mean, so relative to some assignment row, the row that contains selector, yes, and work on those cells, yes, correctly?
Yeah, basically.
Yes, it's very useful. It's very useful concept. I have also implemented this, but without macros when I was writing my Blake2B circuit, because it Blake2B function, it takes a lot of place, and to save the space, I also had to come to this approach independently. So it's very useful, but it has some downside, because if we use this approach from the mathematical point of view, we have to open any column polynomial at many different points, and each polynomial opening adds some field element to the size of proof, and proof becomes greater. Of course, in case of Taiko, it's not a big deal, because, as I know anyway, there will be generated some recursive proof, which will compress the overall proof by itself. So for Taiko, this approach is completely suitable. But in case of some simple circuits without recursion, people should beware that succinctness can be affected a bit by using this, something like this.
Okay, good point.
It's a good point, but also you don't have to use. Well, in practice we do use like lots of rows for like the cell manager. But then, if you're like concerned about the amount of like points you have to open, you could also just use like one row, and you still have some benefits of like some extra abstractions on not having to worry about columns and stuff.
Yes, I agree. If you use a lot of columns, then the degradation of succinctness isn't sufficient. Of course, I agree completely. And the second clarification, is about lookups. I saw the slide with plookup and the fragment of original paper where plookup has been proposed. Actually, in case of Halo2, plookup protocol is not used at all. Halo2 uses its own lookup argument, which is, from my point of view, is a bit more mathematically beautiful. It's easier to understand, and as far as I remember, plookup has some problems with dynamically generated lookup tables, or it's impossible at all. I have read about this more than a year ago. I forget the details, but the lookup argument used by Halo2 is if it allows dynamically generated lookup tables consistent with of arbitrary number of columns without any problems. And from my point of view, it's better that it's easier to understand that original plookup. For one who is interested in the Halo2 lookup argument, I mean, it's mathematical apparatus. I can provide a link where it's described well. Not a lot to read, but still interesting. So that's all. And thanks for attention.
Thank you, Alex T. Any other questions? Yeah.
Okay.
I would like to say thanks for the presentation, Cecilia. It was excellent. I'm curious about the problem about the degree reduction problem. I'm curious if it's like, I haven't looked too much into it, but is it possible to solve it like optimally? Like in terms of these sub-expressions, you want to have the correct sub-expression, so the overall degree is reduced, if I understand correctly. So could you say something about the difficulty of solving this problem?
Yeah, so basically right now it's just like a naive recursion. As you know, like expression, if you look at the structs inside, it's basically like a recursive structure with sub-expression adds other expression or multiply other expression. So as we split this A plus B, like I think it's almost like a leftmost approach where you iterate through like the parenthesis, right? And then what it do first is see this A plus B, and then it will like try to evaluate the degree of A plus B. And now it sees that the degree is actually 1, then it store A plus B as 1. And then you have like the right chunk. At this point, still like you don't know the degree of the right chunk. And then within the code, it's like it's detecting the right chunk. And then it's going further to split this more. So by the end, if you have like a super, super big expression, you have like a right leaning, I'm not sure if you call it left leaning or right leaning tree that's like crippled. You know what I mean? Like this side would be like short, that side would be long. Because it's like everything is reading from left to right. There's no other optimization. If you can like split a tree in some other alternative way, potentially there could be. Yeah, but we didn't implement that. Specifically, like Brax didn't write it that way. Brax just like span it out and that's it.
Yeah, I guess it's a like I'm not sure. I guess you could like brute forces and like try to optimize it. But yeah, it's not only like this expression. It's kind of like, yeah, if you want to really optimize it, you also have like other expressions that will also be split up, which will also have like similar subterms. So yeah, it just gets like very complicated. So there's like a very easy approach where if it's like by chance, if the sub expression is the same and we already stored it, then we reuse it. And that's basically it. That's the only optimization we currently do.
Yeah,
okay,
yeah.
cool.
For example, if there's like another expression with A plus B times X plus Y, and in this expression, A plus B is already stored. And when we're looping through the other expression, then we'll look up and we'll look for the A plus B that should be existing in the array somewhere. And then if we find it out, we'll just like take it out of it. Yeah. So it is reusing some of the expression that we stored before.
Right. It's an interesting problem. It reminds me a little bit of dynamic programming, where you have like overlapping sub problems that you reuse. But I'm not really sure if you can apply the same methods to this particular problem. But it seems like the heuristic you came up with is pretty efficient.
Yeah, it's very
Thanks.
common. Yeah, thank you.
One small question about degree reduction. So, in general, what do? We just store some intermediate results of computation in some other cells. Yes, correctly?
Yes. We store intermediate result and we constrain the intermediate result to be equal to like the partial result of the original equation.
So from the point of view of reusing the same parts, if we have some elementary expressions like degree 1 expressions, while we perform the process of optimization, we can make some hash table of those expressions, and the key of this hash table would be the hash of the expression, and the value will be the coordinate of cell where it's stored. And once during the parsing we encounter some basic expression which have already been calculated, we can just check it by means of hash table prepare the comparison with key, exact comparison or not by hash, and after this, if keys are indeed the same, we can just use the already allocated one.
Yeah. I think in the assignment phase, that's basically how it is done right now. It's like a hash. It's a hash set of all of the assigned value. So if you're looking for some value that already exists when we're like, let's say we're trying to assign this node in the middle, and then we've already stored the leaf node, then we just like hash it and then take the value. But that's during the assignment phase. Because originally, the original implementation was have the entire cell table stored, and then it was like looping through everything to find specific cells. But I changed that into like a hash set, I think, or hash table, hash map. Yeah. So now it's like in the assignment stage, it's actually being done that way.
So you are already using some hash map for this purpose, yes?
Yeah. For assignment,
Great.
yes.
Great,
yes.
Good job.
Yeah, it's on the expression level, right? Because if you can reuse the expression, then that means the state is stored in a single cell. So if you assign the values, then you only have to assign it once. Like, yeah, you don't have to do any fancy things on the assignment level because you already did the deduplication on the expression level. So this one cell will be reused in multiple expressions. So like, yeah, you just have to assign it once. And yeah, that's like a simple list. So
good, exactly the thing I was talking about. Great.
Yeah. Okay, any other question? I guess this presentation had been like too technical for non-ZK people.
Lisa is muted. She's trying to say something.
Oh, I'm sorry. Yeah, I was saying like thank you, Cecilia, again for presentation, and thank you everyone for questions. Anyway, what was it? I don't know if it was too complicated or not, but we will share it on YouTube so more people who are interested in technical stuff will see it. Yeah, and I think we can wrap it up here. Thank you. Much thank you for everyone for coming. Thank you, Korczynski, for quiz, and thank you to all presenters. And a call for everyone who is in European zone. We have one more session in the evening with 2 presentations, one from Brecht and one from Jeff, and one more quiz that is also very important. Yeah, if you have an opportunity, please join us. It will be 7 p.m. Test time, I guess. Yeah, thank you, everyone. See you soon. Oh, and I will send POAPs. I will send POAPs today. That's also very important. Thank you.
Thank you, Lisa. Thank you, everyone.
Thank you, Lisa.
Thank you, Lisa.
Thank you, Lisa.
It was awesome.
Thanks.
Bye-bye.